Here's another thing that you can think about in exploration and mining, episode 4, twin drilling. Today we're going to talk about twin drilling. What is it? Where is it coming from? It's another term that gets bandied around, but what does it really mean? I can't actually find the earliest reference to the word twin drilling. Now, we started the first few episodes to talk about things like verification and validation and replicating and duplicating, and twin hole drilling is effectively something similar. But now we have this word twinning. Where does that come from? So does everybody know what this means? And I'm the only person that wants to know what the history is and what it really means and how to do this well. How do we do this well? Who tells me how to do it well? Is there a book on this stuff? Is there a Bible on this stuff? How does it actually work, and what is twin drilling? Before I lay out what the next 20 minutes is going to look like in terms of laying out this topic of twin drilling, let's have a quick check where this term first started being used. So there is a reference in Peters from 1987 in his work on exploration and mining geology on the term. But there isn't really a definition of this stuff. So what is twin drilling and how do we need to use it? So what I'm going to do in the next 20 minutes is run you through what a bit of a definition is, and I'm sure there will be some comments on that and what you think twin drilling is and how you use it. Would be lovely to hear in the comments, but I'll start with that. Then I'm going to run through the objectives. Objectives are everything. So what we really want to do is understand why we're doing it and what we're trying to get out of it. It's not just a compliance thing, and it's not just a thing that you just do. You have to do this for a reason. So let's really dive into the objectives. Then there's obviously a planning and execution stage as well, because we have to drill these holes. But we have to worry about data preparation as well before we do an analysis. And then comes the dreaded analysis, where we'll make all of our type 1 and type 2 errors, right? False positives and false negatives. So I'm going to run you through that as well. And then later on, we have to make the difficult decision, if there is a bias, whether we're going to correct it and how, and whether we really should do this. And then I'll cover right at the end some bits and pieces in the literature that you could go back to as well. So let's get started. What is the definition of twin drilling? Well, I don't know. There isn't really a definition, and you can kind of imply what it means. Twinning, probably something about making a true copy of something, right? So there is really the implication of this whole duplication, replication thing, and you sort of veer into this world of the verification, right? So we're trying to verify something. So what I like in terms of a definition is this. I call it the drilling of holes very close to existing drill holes for the purpose of the verification and validation of sampling and assaying. It is carried out by a drilling technique that is considered of equal or better quality than the drilling being verified. So that's what I consider a good starting point, but feel free to tweak this and to come back with me with your definition of twin drilling. So let's see what the objectives are. What is it that we're actually trying to do? When it comes to the objectives of twin drilling, there's different ways we can look at this, but let's use some familiar terms like verification, quality control, quality acceptance testing, and validation. All of these things are relevant. So if we split it up, let's start with verification. The most common use, or what we all know twin drilling has been used to, and the kind of time when this first started becoming a thing, is for due diligence, right? Verifying means ensuring that something is true, that it is real and it exists. So when was this relevant? Well, remember Busong of Briax fame, right? People came in and said, okay, this is interesting, there's some great results, but let's verify that this is true, real, and correct. So they drilled some holes and it turned out to be not there, and all the rest is history. So that is a very classic verification thing from a due diligence perspective. And perhaps arguably you're less interested in the minute details of validating RC versus diamond or various other things that I'll get into. But that is a real utility of twin drilling for the pure and simple binary perspective of showing that something is true and real and that it exists. The second objective is one of standard quality control. And again, I'm going to talk more about quality control and what it really is, but this is all about the common practice as you go, as you are drilling, the things that you do to just maintain a control on your quality of what it is that you're doing. You build this into your program of resource definition drilling. That's the second group of utilities, or this family of utilities failures again. So first verification, secondly there's a QC component. For instance, you are monitoring high-grade intersections that really drive models, right? So you're drilling something, you hit your 5 meters at 10 or your 10 meters at 5 and you're happy and you're making your models, your wireframe stuff together. And then you will have some of these intersections where suddenly you get your 40 meters at 50 grams, right? Boom. And those holes really drive models, right? Pit optimizations go down on it and there's 100,000 ounces sitting around a single hole. You've got to control that. So you've got to run through some ongoing checks and balances during your program so that it doesn't become an afterthought when all of those data land on the resource geologist's desk. So you have an ongoing QC component specifically for these high-grade intercepts. Maybe it's a scissor hole, right? Because let's just face it, we call it twin drilling, and that implies that one drill hole is coming here and that the twin drill hole is coming right next to it. Yeah, sure, that's a twin drill hole, but maybe I just want to verify a certain intersection. You know, it doesn't have to be an exact copy in terms of geometry. You can also drill a scissor hole into something and verify something the same way. So to me, that's all part of the same sort of thing that we're trying to do. But as part of quality control, it would be good to constantly have a bit of a check and balance about some of the higher grade intercepts so that you have a handle on that before that gets to the resource geologist's desk. But also you want to get important information on short range geological and grade variability. Again, that cannot be an afterthought. Right? So after the process is done and then you start thinking about it. So quality control to me means constantly looking at the data that you're collecting and then readjusting the model that you have in your mind. Take for instance a classic regolith hosted ionic clay deposit, your rare earth clay deposit. You've planned this on 200 meter spaced air core holes and you're expecting a pancake kind of geometry, and as you start drilling, there's a little bit more variability than you thought. But you wouldn't really see that unless you start drilling at short ranges. This is where things like the cross come into play, right? Where you drill some holes north to south at a very close spacing and east to west, and you have some ongoing information about short range variability. Are they really twin drill holes? Well, in a way, because they're drilled very close to each other. See, so all of this is part of the same philosophy, and that's why the term twin drilling might be completely misleading, because all of this should be better described perhaps as verification and validation drilling, or some form of that. But you would do this as a standard part of your resource definition program. So I call this part of the QC of any program as you're doing a resource drill out, right? So that's objective, that's purpose number 2, if you like. So we got verification from a due diligence perspective, number 1. Number 2, some common practice as you go, quality control during your resource definition drill out. You build this in. Right, but the third one, and arguably the one where most of the pain and misery happens, is this validation drilling. Now, note that I'm using the word validation. This is not to make sure that something is true and whether it exists. Now it's all about definition of the quality. You're testing something, you're checking the quality to see if it is good enough. We've determined it's real, great. Now we're talking about the acceptance testing. Right? The process has run its course, we've done everything right, we had our checks and balances, but hold on, we have all of our RC drilling now and we want to determine whether it is good enough for our stated objective of an indicated resource classification. So what do? Well, we build in these diamond twin holes of some RC holes, and then we're going to statistically test whether these are good enough. And remember, good enough means it's compared to the data quality objective, which is a validation process. And this is very commonly done, and this is probably what most people would affiliate this process with, is the process of validation. A classic example is when you're comparing blast hole data from a pit against a better drilling data set, because it's very important, and when you do your reconciliations of your models at the end of the month, that you do that with data that you know that isn't biased. Another classic example is the air core, right? If you're sitting in a more regolith hosted situation or you're drilling mineral sands, air core is probably your go-to technique. It's cheap, it's quick, but there are some quality aspects. Usually recovery isn't great. So you could come in with sonic drilling or diamond drilling, it all depends. But generally speaking, a better technique. And then the idea is that you statistically check whether the accuracy and the precision of the original drilling is fit for purpose, meaning good enough for your stated objective. And remember, nothing is ever perfect, so we're talking here about relative bias. Right? Diamond drilling has its issues as well, so does sonic, so this is relative bias, not exact bias. So now that we have some objectives, let's go and do some planning, because we do need to plan this properly. If we don't plan it properly, we won't execute it properly, and then we won't analyze the data properly, and it will be a mess. So we do have to consider some important things. So everything depends on the objectives. If you're trying to verify some previous drilling, I'm probably going to plan that slightly differently than whether I'm very specifically trying to benchmark a certain drilling technique. So it depends on what it is that you're trying to do. But in general, number one, choose your drilling technique. Right? So it's important to not just assume anything. RC is a good technique, but it is better to drill diamond in most instances, but not in all. Sonic is a great drilling technique, but it doesn't work in all ground, and there's usually quite a lot of mucking around to get a good sonic meter out of some tricky ground. So before you start drilling, have a careful bit of planning and talk to your drilling consultants to make sure that what you're choosing is really a good technique, because you want to get this right. Your diamond drilling recovery has to be top notch. So talk about fluids, talk with your drillers, try to get the best guys and girls on the ground to make sure that the technique is optimized so that we can get to as close to exact bias as we can. It won't be exact because we still don't know if diamond is still giving us the right numbers. At least it is as good as we can get it. So secondly, in terms of preparation, we have to choose locations, and that is quite tricky. Now you have to really pay attention to this subject, because otherwise you'll end up drilling the holes in the wrong location, and it is not going to be representative of what you're looking for. But what does representative look like? What does that mean? You have to really think about what it is that you're testing, and you have to acknowledge that what you're drilling probably has a whole bunch of mixed domains. It could be geological domains, grade domains, metallurgical domains. There are different things happening there, and if you just start drilling holes everywhere, then you're not quite certain whether you capture all of that variance, right, in those domains. So you probably want to drill enough holes in each domain that you're interested in testing. So cover your grade ranges, but also cover all these different layered subdomains that are sitting in there. Different campaigns of drilling, different drilling styles. You might actually have a mix of air core and blast hole and RC and God knows what else. So you really have to think about all those subpopulations and really plan your drilling carefully. And the more layered subpopulations you have, the more data you will need to get from your twin hole drilling. And we're going to come back to this one. Obviously, in point number 3, you have to get enough of them. And this is the question that we get most often when we get approached to plan one of these, is how many should we drill and how much is enough? That age-old question. So now please, don't be one of the 5% crowd. If I meet that 1 in 20 person on the street, I swear I'm gonna slap him. So it is really important to make sure that we have an idea of how much we need. Now let me quickly explain the basics to how this works when you have to determine how much you need. If you are comparing two data sets, then imagine those two data sets to be represented by a histogram. I'm pretty sure that everybody watching this knows what a histogram is, but here it is on the screen. That's a histogram for population 1. Move that to the side. Here's a histogram for population number 2. Both of those have a mean. So I'm going to compare the two means, and I'm going to see if there is a difference between them. So if on one image I put both histograms together and I draw two lines of the means, I'm going to look at the difference between them. Now you can visually see that there's a difference, and then you can say, well, that's a difference, but we want to do more with that. And these are basic statistical principles. You would have heard of the t-test, where you actually compare the means statistically, and there are only 3 things that matter. There is the variance in both of these data sets, there's the mean itself, obviously, of both data sets, and the amount of sample data going into it. Those are the 3 things. And what you'll see, if the variance is very limited, then your histogram is very narrow. And if both histograms are very narrow, then it's much easier to say that there is a significant difference between them, which is logical, intuitive. We haven't done anything fancy here. But if we have a lot of variance and our histograms are really wide, and we try to compare the means, then intuitively, see, the distance is the same between the two means, but I have more variance. And it becomes harder to say with confidence, this is the key word, that this is a significant difference. In other words, we have to make sure that we limit the variance when we start comparing data sets. And this is critical because when you start drilling twin drill holes into rocks and that have a whole bunch of layered populations, there's all sorts of issues from water to ground to geology to grade to campaigns, you're going to have a lot of variance. And if you're drilling in a gold ore body that is highly nuggety, you'll have even more variance. And then you cannot distinguish between the means and you're going to make a statistical error in your assessment. And this happens all of the time. Now the other component is N, how much data. That's the third component of these comparisons. And intuitively, the more data would sit in one of those histograms, because a histogram for 5 data points could look exactly the same as a histogram for 55,000 data points. You can draw a histogram of 2 data points if you really want to. So the point being, the more data I put in there, the more confidence I have in determining the difference between those means. So you want that to be statistically significant. Now, those tests can help, and yes, we're going to use versions of these t-tests to make our final assessments later on. So you want to have enough data, and the rule of thumb is the more variance you expect, not just in the nuggety ore that you have, but in all the different subpopulations and the issues that you have, even location of drilling. If you're comparing two samples that are 400 meters below surface, chances are that they're not really next to each other, right? So variance, all of that means that there is additional variance. So the actual number, there is no you must use 30, you must use 60. Generally speaking, nothing happens below 30 data points that is statistically valid, but it completely depends on your ore body and the various subpopulations of data. So along that line, so these are some planning rules that you need to consider. Along that line, when you do plan, yes, closer is better. Now, Murad Abzalov makes that point in his paper, although, I think there's better ways to describe it using the variogram, and I think it's a missed opportunity, and I will go into that in a little bit of detail in a minute. But effectively, you're going to try and validate an existing drill hole, so the closer you sit to that drill hole, the better. So you do want to sit within sort of 1-2 meters, right? And it is possible, but drillers don't really like this, right? Particularly when you're using RC to drill right next to something else because it's an air pressure based technique, and then you have all your cracks and your voids, and that might not be good for drill recovery in RC, but a diamond hole should be able to go within a meter of an existing collar, right? And you really want to try and plan it as well as you possibly can. So those are some planning considerations. Right. Next step. Now we need to go through this process. We've planned, right? And now we need to actually think about what it is that we're going to do. And if we take that statistical concept further, it's called proving a null hypothesis. We're going to come up with a hypothesis and then we're going to prove it or disprove it. So here's a sentence that you would use to kind of phrase a null hypothesis like this. The bias between RC and diamond is statistically significant and is solely caused by the difference in drilling techniques. So from a planning perspective, we then need to be mindful how we set this up if you want to prove that exact hypothesis. Now, knowing what we know about some of those planning issues that we just spoke with, you have to consider a bunch of things. Here we go. There are a number of things that we need to be worried about. The assumption, for instance, let's start simple, that diamond is indeed 100% accurate and has perfect precision. It won't. So you really have to be fully aware of that. The second thing that we need to consider is that there will be variance coming from sample location down the hole due to mistakes in general variance in both color and downhole surveying, right? You want to make sure that both colors are GPSed, and when it comes to downhole surveying, you really want to make sure you're working with the best equipment and some good quality controls so that you know that that trace is where it is. So if you're checking a historic drill hole, obviously there's going to be some variance because that single shot drill hole trace is really not where you think it is. So be very cautious about how you approach that as well. The third point is that as I said before, these populations that you're testing, or this data set that you're testing, is itself a nested combination of all sorts of little subpopulations. And statisticians are very sensitive to that because you cannot compare means of a bunch of mixed populations. And the same is true for resource estimation. The same is true here. So you need to consider things like weather conditions in the RC drilling that you're testing. Because when it was raining very hard, you have a lot of wet samples, and maybe only things went wrong in that campaign. There will be presence of groundwater in some areas but not in others, so you need to be representatively checking areas that have a lot of groundwater issues. This is a very key thing, this groundwater issue, particularly with people testing diamond drilling against RC drilling. There's obviously different management campaigns. We both have different geologists and techies working on the rigs, pulling samples off in a different way, or we have different drillers and even different equipment of drillers, drill rigs, right? There are multiple drill rigs and so on. You can keep going with this, you get the picture. So all of these things need to be considered. Then there is the time, obviously, as well, right? The campaigns. You might have an area that's been drilled 5 times over at least 3 decades, and all of those different drill programs have a different set of conditions, operating conditions, and so on. So very difficult when you actually start combining all those variables. You very easily get to 500, if not 1,000 different combinations. And if you try to unpick all of that, clearly that's not going to happen. So you have to make some assessments, and you have to be very careful and transparent when you report on this to say what it is that you have tested. So be aware of variance coming from that as well. So the fourth point is you need to recognize that we also get variance from different analytical sample preparation techniques. Because if we use the example of diamond versus RC, RC is going to be subsampled differently, prepared differently, and maybe analyzed differently at a different time with a different technique in a different laboratory. So when your objective is to actually look at the bias that solely comes from the drilling technique, then you have to make sure that everything after the drilling is the same, otherwise you don't know where the difference is coming from. So you've got to be very careful with that as well. Point number 5, we also have an issue with, and this is a key one, the distance between the RC and the diamond sample, so the distance between the twin holes effectively. And you could here invoke the variogram again as well, and I talked about that in video number 3 if you want to look back at it, and I will come back with a variogram video at some point. But effectively speaking, if you sit at that distance 0 point on the variogram, your variance is as small as it can possibly be between these two samples, the diamond sample and the RC sample. But the moment those samples move away from each other, the moment the drill holes are 2, 3, or 4, or 5 meters or 10 meters away from each other, you now have more variance between these two samples. And all of that means that when you're comparing means, you just have less of a signal to see through all of that additional noise. This is the reason you want to sit as close to as possible to that 0 point so that you don't have as much variance from the variogram to worry about. Again, 5 points of sources of variance here, right? Now, number 6, we also have a problem with variance coming from different sample lengths. RC drilling might be 1 meter or some maybe 2 meter composites, and your diamond drilling might be 20 centimeters, 40 centimeters, etc. So we have to also deal with that. Now, we also have outliers, point number 7, right? Outliers, here we go. If we start comparing means, statistics, outliers, right? If we're doing this a gold deposit and you only have 45 sample pairs in 2 twin drill holes and 1 as an outlier, you might skew all your analysis, so we have to deal with that as well. Number 8, we will have database and transcription errors sitting in there. Remember, what you're testing is an actual bias of the technique, not some data clerk putting the number wrong in the database. So you really want to go back to the paperwork of the RC drilling, if that is what you're testing, and really make sure that it has all been transcribed properly before you blindly start comparing the two. It happens all of the time. Throw away the obvious mistakes, right? Never allow mistakes to enter your statistical analysis. And then lastly, point number 9, these are all sources of potential variance making your life hard in this analysis, is the variance coming from sample support. Diamond core, if it's NQ, generally has a lower volume, which therefore has the higher variance than the RC drilling. But everything depends here, but it's just something to be aware of as well. So a whole bunch of potential sources of variance, and all of that means noise when we're ultimately comparing two histograms. The more noise, the wider those histograms, the harder it is to say something useful about those two means. And you will make a type 1 error, a false positive. So what can we do about this? Well, we can actually do something before. So now we've drilled the holes. So we have been good in our preparation. We understand all the issues. We've been careful with all the work to get to this point. Now we're going to analyze the data. And we have a little bit of preparation to do. The same kind of preparation that a resource geologist would do before they actually plug stuff in the big black box of ordinary kriging in the software, right? You have to do a bit of homework and you have to sort of play with the data a little bit. So not to regurgitate all the previous points that I've made, and you can sort of check the list here and look at the reference articles that I put in the link at the end. But you would, for instance, really make sure that you check all the diamond core recovery, right? And if there's big zones with 20% recovery, you probably don't want to use that to compare against RC. You're going to check your downhole surveys, you're going to look at dogleg severity, and you're going to remove data from the analysis where you just don't have enough confidence that these points are still close to each other. If these points are really 400 meters deep and one of the holes is a single shot survey every 30 meters, throw the data out because you're not comparing apples to apples. Right, we're going to flag the data now for relevant domains, which is easy to do if you already have a model sitting in your software. Now we're going to look at applying sensible top cuts to deal with outliers. We're going to do some compositing, very important. We're going to composite all of this to, say, 1 meter. So now our RC samples are 1 meter and our diamond samples are 1 meter. Now we can start comparing apples with apples. Now the last step in terms of preparation needs a little bit of thinking. Right? Because remember when I said the variogram, the further you sit away from the drill hole that you're testing, the more variance that you have. So we now really want to only select those samples for analysis that are actually close to each other. And people have been writing scripts to achieve this for years. I remember seeing a data mine script at least 15 years ago that did this and was quite a convoluted process. Right? But I wrote this script in Excel about 10 years ago because it's simple trigonometry, but it took about 4 hours to run. And all it does, because the moment you desurvey your drill holes, which means taking the center points of your composite, so now they become points, right? Now I can select the points that I want, but I only want to select the points that are close to each other. So I want to build in a distance buffering, which is a simple trigonometry thing where you look at one point and it compares it to the distance of all the other points in the other data set and selects the nearest to it, which you can do in Excel quite easily, but it just takes a long time to run. So when I thought about this, luckily Rob de Bruin was around, who was the maker of supervisor software that many people watching might be familiar with. And he's developed his own software. And I was talking to Rob about this, and he said, sure, I can do that. In about a couple of days, he programmed this, and now it runs in 10 seconds. And what this does, it makes this entire process super easy. It takes all the desurveyed points from the drill holes. So it has X, Y, Z, and it has a label, RC or diamond, and then the grade. Right? And then perhaps you want to add another bunch of flags for different subpopulations, but assuming that you've selected the population that you want from a certain geological domain, now you have 2 data sets. And the software really just runs very quickly through the data pairs. So now we have data pairs. So we have an RC sample, and the closest sample from the diamond hole sits right here. And now I can extract that and actually call it a sample pair. And that's really important because now we can do some cool statistical stuff with that. Now the problem is you don't know how many pairs you want, so you want to make that an easy process. So here I'll run through a little 2-minute clip in terms of how you can do this in this software and what you can get out of that.
Okay, so here we have a classic Leapfrog working environment where I've only got 2 instances. One is a blast hole grey controlled drilling dataset shown by these pink drill traces here, and the other one is a set of diamond drilling in blue traces. As you zoom in and out, you can see the shape of a pit here, just for orientation's sake. If you zoom in, you can see that the grey control holes are around 5 meters deep, and there's a lot of them. The diamond drilling in the blue are of course much deeper holes, drilled before the pit got started. So what we can do now is look at a section and see where the diamond samples are very close to the grade control samples. Let's zoom in to find a good example. Here's one where the midpoint of a grade control hole is very close to the midpoint of a diamond drill sample. In our analysis later on, we're going to treat those 2 points as true pairs. The first thing that we need to do is to set the diamond composite length. So let's briefly investigate the blast hole drilling depths. We're not going to do anything magical here, just a quick and dirty interval statistics, and you can see that the mode is around 5.35 meters. There's some stuff here on the right, maybe some mistakes and errors, some stuff on the left. Let's not worry about this too much for the sake of this example. I'm going to run with 5.35 meters for my diamond drilling composites. And to create those, I'm going to right-click on the diamond drilling here and go New Numeric Composite, Entire Drill Hole, and then I'm going to simply type 5.35 here. Now, I'm not going to worry about all these settings for the sake of this demonstration. There's much to say on the topic of compositing and what you do with residuals, data caps, and how the minimum coverage works and so on. I'm not going to worry about any of that. Obviously, we're going to composite the gold field, which is the only field in this data set. And yes, there is some missing data here, so we're going to click OK to that, and that runs very quickly. Now we have some composites. Now I just want to make sure that I don't get any negatives and zeros in a data set because I haven't fully investigated this data set. There might be some below detections and some zeros that you have with these big data sets quite often. So I'm going to right-click, New Filter, and we're going to create a very basic larger than 0.001 filter in there. Remember, these are gold grades in ppm. So click OK to that. I've already created one for the grade control data, so now I can go and export both of these data as CSVs for import into X10. Right-click on the grade control assays and click Export. I'm going to select that filter that I made, and importantly, I'm going to add the interval midpoints. Click Save. It's a lot of data, but this runs pretty quickly. And we can do the same on the diamond drilling data. In this case, export that numeric composite, and again, we select our filter and save. Now I'm just going to re-import these XYZ points, just to have a bit of an idea of what it is that we're trying to do. So under points, I right-click, import, and then drag both grade control and diamond samples back onto the screen. Now I've already isolated one particular point that I want to look at, and we're going to just zoom into that straight away and draw a section across that just to understand what is happening with the data here. In this case, what we can see is that there is a diamond drill hole coming through here, and if we switch on the traces and depth marks at 5.35 meters, then you can see that this point is indeed a composite of this interval here. This purple diamond point is very close to the midpoint of this blast hole shown by the green point. Now again, remember that 5-meter composite means that there's a lot of variance absorbed in that composite, right? So just something to keep in mind as we play with our distance buffers later. If you would do this with diamond and RC drilling, these points would commonly represent 1-meter composites. And just to show you how the analysis works, what the X10 software is going to do is create these buffer spheres around these points. And it's going to look for the nearest sample that it can create a pair for. So here's a 2-meter buffer, for instance, around this point. And in this case, these 2 points will be extracted as a data pair. So you can set your buffer to anything you like. It could be 5 meters, could be 10 meters. And at 10 meters, it's going to select more pairs as there are far more composites from either population lying within a distance of 10 meters from each other than there are within a distance of, say, 50 centimeters. Beyond 10 meters, things will get a little bit difficult to compare, obviously, in most deposits, as I've already discussed earlier in the video. So you have to play with it. But that's what we're going to do. Now we've exported the data, it's now over to X10 to start analyzing it. Now we're going to load X10, and you'll see that it loads pretty quickly. I'm loading version 1.4.18, and for those of you familiar with the Snowden Supervisor software, you'll see a very familiar layout. There is a 3D viewer here, and there is a data loader tab here. We will be loading data and taking it one step at a time. You can right-click on data here, and since we have exported the data as CSV files, we will select text here, and we will start with loading our diamond sample composites here. Now, I don't need the ID of the holes, I don't need froms and tos, I just need gold grades and I just need X, Y, and Z. We don't have to set any conditions on the data either here. I could have also dealt with a grade validation here, but all the data should be excluding the below detections and the zeros. So I'm just going to click load, and as a quick check here, we can see indeed that the minimum gold value is 0 and that the coordinate ranges look reasonable. For the grade control dataset, we follow the same process. I don't need the whole IDs, I just need gold grades, and I'm just going to click load. A quick validation shows again that everything seems to have loaded here as well. Now we have two instances that I can work with, one desurveyed grade control dataset and one desurveyed diamond drilling dataset. And it has the X and Ys and the Zs, and it now just needs to run the pairing process. So what I'm going to do is right-click on data once again, but now I go to add and find a distance subset module. We now need to tell the module which two datasets to use, which we can do right here. So we're going to use the assay data from the diamond sample points, click OK, and the same on the other side for the grade control sample points and hit OK. There are a couple of things to point out here. The max separation distance is defaulting to 10 meters. This means that the module is not going to select any samples that are more than 10 meters from each other. 10 meters is a reasonable distance to limit the analysis to, because if you make that larger, you're really starting to mix your populations and allow too much variance from the variegram to come into the analysis. In our Leapfrog project, for the single sample I'm using to explain this, it is that blue sphere that I was showing. The other option is to find nearest pairs only. If you select that, then for each sample of dataset 1, it is going to select however many samples from dataset 2 that fall within that circle. If you leave that unticked, then it is going to select any and all samples from both datasets that fall within this sphere. I tend to use the paired data only option, as that allows me to run paired statistical tests on the data. But it does depend on your dataset, and I suggest you play with this. There are various ways you can now run the analysis, but I tend to click this button here to run an update. For very large datasets and large distance buffers, this may take a while, but this should be done anywhere between a few seconds and a few minutes, depending on the power of your computer. Now that it's finished running, the results appear here on the left-hand side. We can simply click any of these items to inspect the outcomes. I usually start with the QQ distance view right here. Now I'm just going to quickly rearrange the window layout here to give us a little bit of a better view. And now that that's done, you can see a QQ plot in the top left, and in the top right is a bar graph showing the amount of data points at each incremental distance step. Some further fiddling is still required. I like setting my goal axis to log scale, for instance. These are the amount of true pairs that we get as we increase the buffer distance from 1 meter to 2 meters to 3 meters and so on. The QQ plot showing is for pairs within 2.2 meters, but if you drag this slider, then the QQ plot is automatically updated as you decrease or increase that buffer distance. Pretty neat. There are 11,000 pairs at a distance of 2 meters here. The two distributions, diamond drilling and RC drilling if you like, appear to be pretty similar as judged by the close to 45-degree line that you can see here. But the line does depart a little bit from the center line at low grades and at higher grades. The spike here is just a single outlier. Recall our requirement to deal with outliers before we analyze. But does that change if I either move the distance to 1 meter or to 10 meters to select participating pairs? You can use the slider to check. The bias increases a little bit more here. I see fewer pairs, but 1,600 pairs is still a lot of data to work with. I usually restrict the distance as much as possible while still staying above, say, 100 paired samples for your average gold deposit for a robust conclusion. In this case, we have 1,600 pairs and a mean of 0.89 versus a mean of 0.98 for the other data set. So there is an indication of a roughly 9% bias sitting in those data here at around the mean grade of the deposit. It is up to you to determine whether this is material. Now, as I open up that window, more sample pairs will come in. You can see the number of pairs keeps going up and that the shape of the QQ plot remains rather stable here. So that's a good thing to see and allows for a robust conclusion. There are, of course, many different ways that one can look at a QQ plot. And once again, be careful with drawing conclusions from this. I'm not going to go too deep into the analysis here, as I haven't really gone through a full data preparation and cleanup. This is just to show the process in X10. Now, another way to look at the data is by investigating this box and whisker plot here. First, I'll set the y-axis to log scale, and then I can see that it tracks the medians, means, and quartiles of the diamond and RC, if that's what you're working with, sample pair distributions for each distance increment. This allows you to see if the median or mean differences change as the distance setting changes from 0 to the left to 10 to the right. The key here is to look if the relationships change as the distance buffer increases. In this particular case, they appear to be rather stable, which means more support for any conclusions that you may draw from these QQ plots. I can also inspect the pairs in the 3D viewer. You can even bring this 3D viewer onto a different screen. And then as you drag the slider on the distance graph left or right, you can see the pairs automatically updating in real time. Also pretty neat. You can also export the pairs as CSV points for importing and further checking in your favorite mining software package and for further processing for statistical differences. Also, just to note that a new version of X10 is about to be released at the time of release of this video, and some of what you're seeing on the screen here will be vastly improved in the next version.
So now at any chosen buffer distance, we can extract pairs very quickly, and then we can do all the usual analysis on this that we want. It's a super easy process, and we can also visualize the data pairs in our 3D software, which gives us a nice handle on what we've actually selected. So let's get to that part, the analysis. Now what do we do, right? There's a lot to consider before we get to this point, but now we still have to do this really, well, it sounds simple. Let's just create a scatter plot, right? Easy. This is super simple to do, and we even know how to make a QQ plot. But be very careful, right? Because we're primarily looking at bias, although I will come back to variance as well. So what do we do now that we have paired data? Well, everybody knows how to create a scatter plot. So that's what we can do. Just put one data set on X and the other on Y, and put a line through there if you really want to, and have a quick look, right? It's a good starting point. It's not where we want to end, but you can do this to just have a look. But remember, when we're dealing with this whole bias story, a bias is almost never consistent, right? So you got to look at the data in different ways. Don't just click the buttons. Think about what the process is and where maybe in those mixed populations that you're still trying to check, right? There might be a bias low in the low grade and a bias in the high grade, or there might be three different things happening. Be careful. Don't blindly compare the means of both data sets. So a scatter plot is a great way to start. Use it, but don't draw any conclusions from it, right? Just some observations about some potential trends that you might see. That's what you're trying to do. So a QQ plot is also useful, but what I've noticed over doing this for some time now, it is very dangerous because you are so prone to make the wrong conclusions from QQ plots, right? It looks like it's very close to that 45-degree line, but it's actually showing you a bias. All right, so be very careful with that as well. Look for trends in that one as well. Now, what I like to use is one step further. We can use non-parametric paired t-tests to see if across the entire grade range, so if you make a few assumptions on whether you're actually looking at a single data set, and then you can use like an alpha of 5%, if you remember your t-test from high school, whether there is a statistically significant bias between the pairs. So that's not looking at the entire population and difference between the means. This is a paired t-test. And a standard pair t-test you can't apply to a skewed range, so you have to use a non-parametric t-test, such as the Wilcoxon-signed rank test. But there's other things as well. You can transform the ratio between RC and diamond and then transform it to a log, and then you can run a single-sided t-test. There is a bunch of other things you can do. I don't want to get into the detail, but you can do some cool things that get you a little bit further than the stargazing of the QQ and the scatter plots. Using these calculations, you can actually see if there is a statistically significant difference, right? The p-value that you compare to the a value. And you get other exports out of that formula, like the effect size, so you can have a little bit of a discussion of how big that difference is. And there are other things that you can do, like the probability that one is higher than the other. And it allows you to kind of phrase the language about the issue that you think you're dealing with. Okay, so very useful. There is an online RSC data quality management app in development together with Max Geo's datashed that will soon come out, and you can do all of this stuff online. So look out for that. Now, look at the subpopulations in your QQ plot and recalculate those t-tests based on things that you see, trends that you see. So you might do the same calculation only for the lower grade where you see a certain trend, or the higher grade or above cutoff and those kind of things. So play with that and run it again. Increase the buffer distance. Look at more samples coming in. Remember, if you increase the buffer distance, you get more samples, but you get more noise because you're including more in different domains. If you reduce your buffer distance, you get fewer samples, so your N comes down, but you reduce all the noise. Somewhere between there, the needle sits at a place where you get a reasonable signal coming through. This is not exact science. This is why you don't have to blindly click the buttons, because you will end up making a type 1 error. Play with that, look at all the options and see if the signals coming back mean something to you. Right, now when we have bias sorted, right now we have an assessment, we have paired data from our twin drilling, great. We can apply some tricks to that. We do a lot of preparation. Then we assess this with a non-parametric t-test and some QQ plots and some distance buffering. Great process. How about variance? Right? Well, variance is, you can't do too much with that, but you can certainly check the downhole variograms for both data sets, right? You do want a similar variance coming out of that as well. So maybe there's no bias between the two, but if you look down the hole from one sample to the next, and you look at the average variance between every subsequent sample, you might get a different variance in the RC drilling than the diamond drilling. And if you want to get fancy, you can even run a Fisher test to check whether the difference in variance is actually statistically significantly different, instead of you looking at two variograms of downhole plots and go, that looks good. So you can do stuff with variance as well. Now lastly, maybe I have established a significant bias. Now what? Right? Because we still have to do something. If you're a consultant, you still have to make recommendations. If you're working on the ground, you still have to tell your bosses whether we have a problem. Now remember, classification is your friend. The world doesn't have to end if you have some bias, but you do have to be very careful. Now, there's a couple of things you can do. Correcting for bias, Abzalov actually talks in his paper about it. Be careful with that, because a bias is never consistent, right? So correcting it will probably fix one problem somewhere and create two others somewhere else, and you don't know where you're creating those problems. So you could do a multi-order polynomial correction on the QQ plot, which is really simple to do, right? Even in Excel, right-click formula, get a formula out of it, and you could correct for the bias. Right, and if you do this on the QQ plot, effectively it's declustered, so it's a reasonable correction. Now, don't worry, resource geologists, don't freak out. We're going to estimate with this, but not from the purpose of reporting this. This is your sensitivity testing, right? So correct the data and then estimate into the blocks with all the same conditions in the variograms, in the distance search ranges, in the minimum samples, blah blah blah, and do the same for your corrected data. And then look at your grade tonnage curve and look at the tons and ounces above a cutoff grade and see if it's sensitive to that. That actually allows you to say something useful about how important this bias really is. Because remember, even if something is statistically significantly different, it may not be material to the project, right? Remember, classification is your friend. So when you do run that comparison, you're going to look at the difference in your block estimates, and you can say something useful about it. And you can do all sorts of things, because you can look at the blocks where the difference between RC and diamond is the largest, and maybe they sit in one particular area. You can pick a threshold, if you like, of some sort of relative difference, and then you select that area and say, well, that might be inferred, or maybe we need some more drilling there, right? This is a great way to work with twin drilling. You could also, for the twin drilling that you have, run an estimate in 2 blocks, only with the RC twins and only with the diamond twins, if that's what you're using, and run 2 estimates. And then you could do the same thing again. Are they very different? Are they very different above cutoff grade? What conclusions do you draw out of that? Remember, none of this is exact science, but none of this stuff on twin hole drilling is covered anywhere in the literature. And all these things are not really covered in the JORC Code and the CIM guidelines. However, in both those documents, there is a mention of twin drilling, but just a single mention with no explanation. So there are no resources that tell us what to do. However, there are some papers, and here I go again, because papers have relevance. Some people have thought about this before, right? And in this case, here's a quick list, but I already mentioned Peters' document. There's obviously Annels' book, and there's some other reference here. Sinclair and Blackwell is another famous reference. Abzalov has put a paper out on twin drilling, the only paper that I could find anyway, on twin drilling specifically. And he repeats that information in his 2016 book, Applied Mining Geology. Again, I'll put a link in the description, and it is section 11. Then we have one more paper that referenced some of that stuff that is working on it, that is talking about a case study, which is also quite a nice read if you want to know more about this. So I'm saying we are on uncharted territory a little bit here, right? There isn't a lot of theory out there of exactly what to do. How do you analyze the data? Is everybody doing the same thing? What is good practice, right? And I keep talking about the difference between common practice and best practice. So what do we need to do here? This is the process that we apply with RC, and there's always more to learn. Every deposit is different. You'll have different methods. I'd love to hear more about them. Please let me know what you think in the comments. Please be constructive. We all have stuff to learn. You'll have great ideas. Let's put this together and come up with the best way to analyze twin hole drilling. See you in the next video. If you like this video, there's more to come, and there's always new things to talk about. So please throw us a like and a subscribe, and we'll see you in the future.